Alright, so for the review today, I'm going to go over a few of those questions that were talked about on those review cards. So the first one I want to start with is question number 1. So calculating the pH at each point of the titration. So we have a titration of 30 milliliters of this 0.0700 molar NaOH with 0.200 molar of HCl. Alright, to attack this problem, the first thing I see is that we have a strong acid with a strong base. So I'm going to go ahead and I'm going to make note of that. Let's see. Strong acid and strong base. This is going to be important to notate because this is what's going to help us guide how we find the pH at each of these different points of our titration. But the first thing I want to do is I want to write the chemical reaction between the titrant and the analyte. So in this case, I'm going to have OH minus from the NaOH plus H plus from the HCl gives me H2O. So this one's a fairly simple one, and we do note that it is 1-to-1. And the next thing I want to do is I want to find VE. So remember that VE is the volume that we need to reach that equivalence point. And to solve that, we're just going to do like an M1V1 situation. So I'll say 30 milliliters times 0.070. And so our VE in this case is 10.50 milliliters. Alright, so for every titration problem that you're going to see, this is how I would start. Notate what you have in your titration, write out the reaction, and then find your equivalence point, because that's going to be very important to figure out the next few steps. So the first thing we want to do is we want to find the pH when we are at 4.50 milliliters of our titrant added. So that means that we are before VE. Alright, so before VE, I'm going to work out these streamlined calculations just because that is what makes sense to me. But you can also do this by finding the moles and going about it that way. It's really whatever is best for you. But in this case, if we have 4.50 milliliters of titrant for before VE, that means we have an excess amount of that OH. So I'm going to use that streamline calculation, and that's going to be OH minus is that fraction remaining times the initial concentration of OH times the dilution factor. Alright, so the fraction of OH remaining, that is the VE minus V added over VE. So in this case, that's going to be, what was VE again? 10.5. So 10.50 minus, we have added 4.5 milliliters over VE, which again is 10.5. Our initial OH concentration, if we go back up here, is this 0.07. And then our dilution factor, that's the initial volume of OH over the total volume of the solution. So initially we had 30 over, now our total is 30 plus we've added 4.5 milliliters. Alright. And when we do all of this, we end up getting that OH is 0.03478 molar. And so from here, we can go ahead and get that POH and then find pH from there, if that's how we would like to do it. Or you can plug this into the KW equation. So you would do KW over the OH concentration to get you the concentration of H. I'm going to do the KW. So if we have, let's see, we have KW equals H plus times OH minus. Then we know that H plus is Kw over our OH concentration. So if I do it this way, then I would say that H plus equals 1.0 times 10 to the negative 14 over 0.03478, which equals 2.88 times 10 to the negative 13. So pH equals 12.54. Yay. Okay. So thinking about this, what we needed to know that was going to be helpful is definitely this. So this is something I would write down on that cheat sheet. And even writing, like, when I have a strong acid and a strong base, before VE, we have excess OH, so I'm going to use this streamline calculation. Or if you like to work in the moles, you can write the steps you need to find your moles at this point. The next one is going to be at VE. So when we are in a solution with a strong acid and a strong base, at VE is actually pretty nice. We can think of it this way, where if we had, this is our reaction at this point, and pH is determined by the Kw. So we can say, we know that Kw is OH minus times H plus. And at this point, if we label these X and X, we can go ahead and do that here. We'll see that Kw equals X squared, and we know Kw is 1.0 times 10 to the negative 14 equals X squared. So I'm going to take the square root of that, which is just 7. Well, this is 1.0 times 10 to the negative 7, but this is H plus. So we plug this in to the negative log. Then this just equals 7, which is our answer there. So this one's pretty easy, but this only works when you have a strong acid and a strong base titration. So keep that in mind. Let me make a note. Only strong acid and strong base. Okay. And lastly, for this one, we want to find it after 11.5 milliliters of our titrant have been added. So at this point, we are past VE. I already forgot what VE was, 10.5. So we are after VE, which means that we have a diluted HCl solution is what we're working with. So there's excess H plus, and in this case there's 1 milliliter excess of H plus. So to solve this, once again, I'm going to use that streamlined calculation. Again, you can do this with moles if that makes more sense for you. But for the streamlined calculation, this is where we're going to do the initial concentration of H plus times that dilution factor. And that dilution factor is found the same way we just found it earlier. So this is going to be the initial concentration of H plus was 0.2. And our dilution factor, again, is our volume of excess. So in this case, we have 1 milliliter excess over the total. So this is going to be 30 plus 11.5. And when I do this, this should give me 0.004819 molar. And from there, since we are already finding H+, we can just plug this into the pH. So pH equals the negative log of 0.004819, which equals 2.32. And then if we actually look at the values of our pH, we can see that they are going down as the titration goes on, which makes sense because initially we have a solution of this strong base and we're adding that strong acid to it. So that solution should get more acidic. The next problem I'm going to work is problem number 2 from those review cards. So again, we're wanting to find the pH at different points of a titration. And now we have 50 milliliters of 0.250 HClO with a 0.250 molar NaOH solution. So I want to first start by kind of annotating what we have before I even begin. So I know we have an analyte of HClO, so this is what's in my flask, and it's being titrated with NaOH. So it's important to note that HClO is a weak acid. So now we have a weak acid being titrated with a strong base. This is a strong base here. So we have a few different steps that we're going to want to take, a little differently than how we did the first problem, which was a strong acid with a strong base. So I'm going to start with very similar first steps. I'm going to first write out the full reaction, and I'm going to find VE. So in this case, I have HClO reacting with the strong acid, and it's going to give me ClO minus and water. And then to find VE, I'm going to do the same thing. M1V1 equals M2V2, and I'll find that VE equals 50.0 milliliters. And this, a little shortcut you can see is that since these concentrations are the same, then that means our volume has to be the same for VE. But the first part asks, what is the pH before any base is added? And so in this case, let's think about what we actually have in solution. So if we have, this is just the bottom flask. We haven't added any of our titrant yet. And in here we have that HClO. And HClO, like we said, is a weak acid. So right now we just have that weak acid solution. And in previous learning objectives, we learned that finding the pH for a weak acid is done using that Ka value. Specifically, Ka is x squared over F minus x. And to kind of show you where I'm getting this from, if we were to rewrite that equation, right now we just have HClO, right? So this breaks up into H plus ClO minus. And so this is the F minus x, this is x, and this is x. That falls into this. So I'm going to take our Ka, and we're given that Ka value. So I'm going to say that 4.0 times 10 to the negative 8 equals x squared over, and I'm just going to do the approximation. So I'm just going to have the F. And so in this case, F is 0.250. So that means x is equal to the square root 4.0 times 10 to the negative 8 times 0.250. And this should give you 1.0 times 10 to the negative 4 molar. And then something that's important to note is remembering what x equals. So we have this x value, but where did that come from? Well, right here, since we wrote out the equation, it's easy for us to see that x is H plus. So I can just take this x value and throw it into the negative log. So pH is the negative log. And that tells me that pH at this point is 4.00. All right. So after that, it wants us to find after 15 milliliters of KOH is added. So this is going to be before VE. And so what we're going to do here is we want to think about what actually is this solution. So we have some of that HClO, and we've now actually added some OH, and we have a buffer. So at this point, we have a buffer. If I could spell it, that would be great. And anytime we have a buffer, I hope that we think of the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of A minus over HA. All right, so let's take that. I'm going to rewrite our equation. So that's going to be HClO. We've now added some OH. Gives me ClO minus plus H2O. Okay, and let's see. If we know that this is our Henderson-Hasselbalch, let's figure out what we have. So we don't have pKa directly, but we can find pKa from the Ka. So that means that pKa is the negative log of our Ka, which is 4.0 comes to negative 8. So that means pKa is 7.398. So we have this, and we can find A minus and HA. I'm going to use that fraction method that we saw in class just because that worked well for me. So let's see. At this point of the reaction, at the beginning, we had, because remember, at the beginning it was just this HClO. So we had, all of it was this. So I'm just going to say 50 out of 50. But then we added 15 milliliters of that OH. I'm doing 15 out of 50 because 50 is that equivalence point. So when we add this 15 is going to react with this HClO. So now we have 35 out of 50 remaining with that HClO. And this is also going to get turned into some of that ClO minus. So we have 15 out of 50 there. All right. So with these numbers in mind, I can go ahead and plug these directly into Henderson-Hasselbalch, where this is A minus and this is HA. So I'm going to say that pH equals 7.398 plus the log of 15 over 35. I'm going to go ahead and just ignore these denominators because they're just going to cancel out anyway. And this is going to tell me that pH equals 7.03. Okay. The next one says after 25 milliliters of KOH has been added. And so again, we are before VE. But we are at a special point before VE. We're actually at 1/2 VE. So this is 25% is half of 50. And this is going to be an important thing to note because at 1/2 VE, we have learned that pH equals pKa. I'm highlighting this because you should write this down on your cheat sheet. For a weak acid and a strong base, at 1/2 VE, pH equals pKa. So this is really quick and easy because then if we know pKa, we can say that pH just equals 7.398. Now to prove that this is true, you can do the same steps we just did with the buffer, because this would technically still be a buffer, but you'll find that you end up getting a log of 1, which is just 0. So that's how we ended up getting that pH equals pKa. So you can prove this to yourself if you're feeling uncomfortable with this just being a fact. I tend to feel uncomfortable with things just being quick facts, but you can prove it to yourself. But for the next one, we are at VE, so 50 milliliters of KOH have been added. So at this point, we now have a weak base in our solution. So we originally had, remember we had that HClO in solution, and now we've added 50 milliliters of KOH. So the HClO solution has turned into a weak base. And so, if you remember from previous units, when we have a weak base and we wanted to find the pH of it, we're going to do that Kb. So let's see, we're going to say at VE, we're going to say that we have a weak base. And so I can say Kb equals x squared over F minus x to find the pH of a weak base solution. So I'm going to write out that equation again, and we can find all the variables we need to solve this Kb. So if we have HClO plus OH minus gives me ClO minus and H2O. I'm going to work this out with those moles. So first I need to find my moles of HClO. Well, thankfully we were given everything we need to find that in this equation. So I'm just going to do 50, I'm going to turn that into liters. So 0.05 liters times 0.0250. And that's going to tell me I have 0.0125 moles here. And as this reaction goes on, we're going to add the same amount of moles. these are going to go away, and we're going to end up with 0.0125 moles of ClO minus. All right, and we're going to be able to use this as this F value here. The other thing we need to do is we have to find Kb, and we're given Ka. Hopefully you remember how to do this. So if we have, let's see, Kw equals Ka times Kb. So that means Kb equals Kw over Ka, and we have both of these. So we should get that Kb equals 2.5 times 10 to the negative 7. So now I'm good to go ahead and just plug everything in. So I'll say 2.5 times 10 to the negative 7 equals x squared over F. I'm just going to do that approximation again. And this, ooh, do I want to do this in moles? Yes, I do. Okay. I'm not going to do this, actually, I lied. I'm not going to do this in moles. I'm going to do this in concentration, so 0.125 molar. But to show you how I did that, I took these moles. And I'm going to say that F equals 0.0125 moles. And we are currently in 100 milliliters, right? We have the V initial, which was, what was V initial? 50. And we've added 50 more, so we have a total of 100. So this is just going to be 0.1 liter or 100 milliliters. And this equals 0.125 molar. So that's where this value comes from. Okay. And so from there, I can just say that x equals the square root of 2.5 times 10 to the negative 7 times 0.125. And that is going to tell me that x equals 1.8 times 10 to the negative 4. And remember, we have to remember what this x was. So in this case, x comes from this OH value. So this is not our H+, this is our OH concentration. That looks really, okay. And so we can do POH equals 3.75. So then 14 minus 3.75 equals 10.25, which is our pH for the solution. All right. And the last part is it wants us to find it after 60 milliliters of this KOH have been added. So we are after, well, this is not again. Yeah, this is our first time after VE in this case. After VE. So in our solution, we have diluted excess strong base. Diluted excess strong base. And so what I can do is I can use that shortcut method again, where our diluted excess strong base equals our initial concentration of our base times that dilution factor, which is V added minus VE over V total. So this is 0.250 times, it's going to be 10 over 110. And this equals 0.0227 molar. So if I plug that in to the negative log, I can find that POH equals 1.6435. So pH equals 12.36. All right. So if we look at all of our values, we can see we started at 4 and we got higher along the way. And that makes sense, right? As we're adding that strong base, we should be getting more basic pH. A few things that would have been helpful to write down would be remembering what to do when we have before base is added, knowing that before VE, we are at that buffer. When you're at 1/2 VE, pH equals pKa. When you're at VE, you're going to want to think about what kind of solution you have. So we have that weak base, so we can use that Kb. And then after, we're able to use that shortcut. So I would just take all of these and write them in a little section on your cheat sheet to help you remember what to do when you have a weak acid being titrated with a strong base. All I want to work is problem number 4 from those review cards. So we're asked a 50 milliliter solution of 0.95 molar diprotic base B is titrated with 0.95 molar HCl, and then what is the pH when 75 milliliters have been added? And we're given some pKb values. And so hopefully you've noticed a trend. This is our third problem where we're given a titration and we're wanting to find the pH at a specific point of that titration. So that is a pretty common theme because that's a lot of what we did this week. And thankfully, Dr. Williams provided some really nice tables that talk about the different regions of the curve, and then what the solution characteristics are at that region and what determines pH of that region. So if you haven't written those down on your cheat sheet already, I hope you do that before Monday, because that is what is going to help us with all of these problems. Okay, but when we are digesting this problem, the first thing I want to annotate is what we have in solution: diprotic base B and HCl. And this problem is kind of vague, but I will tell you that this is a weak base, and hopefully we recognize HCl as a strong acid. So we have a weak base being titrated with this strong acid. And we also have some fun information because this is a diprotic base. And even if it hadn't told us that, we do have these multiple pKb values. So that's telling me that we have a diprotic titration going on. And so we need to, when we find VE, we need to find not one VE, but 2 VEs. Now, don't let that scare you immediately. We're going to still have the same first steps and honestly a lot of the same steps that we've been doing. It's just slightly different. So I'm going to start by first writing out our reaction. Again, this one wasn't very, it was kind of vague in what we actually have in our solution. It just said diprotic base B. So it's going to be BH plus, we added that strong acid, and it gives me this BH2 2+. And then I also, again, want to find VE, and like I said, we need 2 VEs because we have the 2 pKbs. Remembering that our curve looks something like this, right? You have a VE and a VE. Okay. So I'm going to find that using the M1V1. So let's see, we have 50 milliliters times 0.95 molar. And then what is our VE? We have 0.95 molar HCl. And we should get that VE1 equals 50. And VE2 is just double that. So in this case, VE2 is 100 milliliters. Okay. So now that we have some of this information, we can kind of figure out where we are in our curve. So we have 75 milliliters of HCl added. So we have more than 50, but less than 100. So that means we are between VE1 and VE2. And so if we wrote down that chart that Dr. Williams talked about, you'll see that between VE1 and VE2, that some of the BH that we have, some of this has been converted to BH2 2+, and we have a buffer. So I'm going to write this in big letters again. We have a buffer. And hopefully you're all saying it with me that means we're using the Henderson-Hasselbalch equation. So we're using pH equals pKa plus the log. It's going to look a little different now because we have this B, but it's same concept. BH plus over BH2 2+, where this pKa belongs to this bottom one right down here. Okay, so this one is just a little tricky because we have to conceptually think about what has happened, but I'll walk you through that. So like I said, some of that BH plus has been converted to BH2, but at 50 VE, at VE1, at 50 milliliters, that is when, so at 50 milliliters, that is when all of the B has been converted to BH. And now we've added 25 extra milliliters, so I'm going to kind of ignore this in a sense. And so at 25 milliliters, some of this BH has been converted to BH2. So I'm going to do the same, I'm going to solve this out using the same fractions that we've been using for the last few problems. And I just want to keep these notes in mind, because that's how we're going to figure out that fractional composition. Well, I don't want to say that, because fractional composition goes with EDTA. That's how we figure out the fraction that we're having here. Okay, so like I said, so some of this BH is being converted to BH2. So if we have 50 out of 50, 25 milliliters of that 50 come from the H plus, have been converted. So now we have 25 out of 50 left here. We have 25 out of 50 over here. And so what I'm going to do is I'm going to use these values in my Henderson-Hasselbalch equation. Now there's one more step we need to do before we can just plug and chug with Henderson-Hasselbalch, and that is this pKa. We're given pKb, so we have to kind of solve for that. And like I said, this pKa goes with the bottom one. So if this is pKa1, that means pKa1 is going to go with pKb2. Hopefully you remember that. There was a relation where pKa1 times pKb2 equals pKw. So that's where this relationship is coming from. But if pKb is 7.43, pKa1 is going to equal to 14 minus 7.43. So that equals 6.57. All right, we finally have everything we need to plug into that equation. So I'll say that pH equals 6.57 plus the log of 25 over 25. Again, I'm just going to get rid of this little 50 down here just because it's going to go away anyway. And maybe you're recognizing that we have 25 over 25 in our log, which is just 1, and log of 1 equals 0. So at this point, pH equals 6.57. Okay. That's kind of a lot of work for a simple problem, but it's good to know the concepts behind why this is the pH. Problem 5 from those review cards. And this is that Kjeldahl analysis that we did. And in all honesty, this is one of my favorite titrations to do. I don't know why. I just think it's kind of interesting that this is how we can find the mass percent of protein in something. But it sounds kind of difficult. There's a lot of words up front, but it's actually relatively simple. So let's first start by kind of digesting what we have in this problem. So the first thing that's going to be important to know is the initial amount that we had in the sample. So we have 0.8087 grams of this chicken sample. It tells us it undergoes this Kjeldahl analysis. So some of that sample is converted to NH3 with the H2SO4 and then distilled into 25 milliliters of 0.7821 molar HCl. It's a lot of words, a lot of chemicals. What's important is the 25 milliliters of 0.7821 molar HCl. Then it tells us that this HCl is back titrated. That's important to know. That's supposed to be 5.89. Nope, that's a 7. Okay, 5.87 milliliters of 0.04521 molar NaCl. That's important. This will be important at some point. And then it wants to know what is the mass percent of protein in the sample. So, whenever we think of this Kjeldahl method or even this like back titration, what we want to remember is there was like a nice little picture that was drawn in class where when we have this back titration, what is happening? We have some amount of HCl. We're adding this known amount. We're adding a known amount of, not HCl. Okay, we're adding a known amount of this NH3. Right, that NH3 is going to be used, that's what we have right here. so that chicken sample is converted to NH3. We don't know this number. That's what we're trying to figure out. All right, and then we add an excess amount of HCl. This is a known amount of HCl. And then we're going to titrate this excess amount with NaOH. So the part that we don't know is this part right here, and that just happens to correlate with this NH3 above it, right? So what we need to do to solve this problem is a few things. If we know how much HCl is added, we want to find our moles of HCl. We know how much NaOH is added, so I want to find my moles of NaOH. And then to find this little missing piece right here, which is our moles of NH3, we're going to take the moles of HCl, because that's what we have in excess, minus the moles of NaOH, and that's going to tell us our moles of NH3. And then, if we were to break apart NH3, you would see that for every 3 hydrogens, we have 1 nitrogen. So for every 1 mole of NH3, we have 1 mole of nitrogen. And at the end of the day, we are thinking that protein is 16% nitrogen by mass. So when we find the amount of nitrogen we have, we can then determine the amount of protein we have. So it's a lot of words, but if we can remember this concept and what this is telling us, that is going to be the biggest lifesaver. So what do we do with that information? We write that on the cheat sheet. So please write that down. That's going to help a ton. But let's go through and actually solve this now. So let's start with those moles of HCl. We can get that right here. So to find that, I'm going to do, moles of HCl, 0.025 liters times 0.07821 molar. So it tells me I have 0.001955 moles of HCl. Alright, then I want my moles of NaOH. I can get that right here. Oh wait. Oh, I don't know why I wrote NaCl. That's crazy. Anyway, that is NaOH. Yes, the excess HCl is back titrated with 5.87 NaOH. Okay, sorry. But that means our moles of NaOH are going to be 0.00587 liters times 0.04521 molar. And that gives me 2.65 times 10 to the negative 4 moles of NaOH. Alright, so at this point, we have done this. We've done this. And so we are right here. So our moles of NH3 equals 0.001955 moles HCl minus 2.65, so negative 4 moles of NaOH. And so that is going to give me 0.001, oh, nope, looking at the wrong number. 0.00169 moles of NH3. And then remembering, in this case, 1 mole of NH3 gives me 1 mole of nitrogen, so I can go ahead and say that this is 0.00169 moles of nitrogen. And then I'm going to go ahead and get that to grams. 14.007 grams of nitrogen. Give me 1 mole of nitrogen. I just got that from the periodic table. And this is going to give me, let's see, 0.00169 times 0.0237 grams of nitrogen. And there's a few ways you can do this. You can set this up as a dimensional analysis. So if I have 0.0237 grams of nitrogen, I know that 16 grams of nitrogen give me 1 gram of protein. That comes from this 16% by nitrogen. Oh, sorry. This should be 0.16 grams of nitrogen. And so that would tell me I have 0.148 grams of protein. If this way did not make sense to you, another way you can do it is you can set it up like 16 grams of nitrogen are in 100 grams of protein. So if I have 0.0237 grams of nitrogen, how much protein do I have? And when you do this, you should get the same value, 0.148 grams of protein. And so now to find finally what it's asking for, which is this mass percent of protein in our sample, I'm going to take what we have from our sample, 0.148 grams, divided by that original amount, which was 0.8087 grams of our sample, times 100, and this is going to tell me it is 18.3%. So that was kind of a lot of work, just because we were just finding moles over and over and then just doing some dimensional analysis. But again, the concept itself is going to be relatively simple if this part makes sense to you. So try talking through that, working through that, and then see if you can get this 18.3%. Work is, I believe, question 9 from your review cards. And this is that really long problem about finding the percent composition of mass of each metal in a pewter sample. So there's a lot of words in here. Instead of writing it all out, I kind of annotated it and drew out what was happening, and we'll walk through it this way first. So it tells us that we have a 0.4477 gram pewter sample that contains lead, copper, zinc, and tin. And it was dissolved in acid and tin was precipitated. So that's what's happening here. Tin has been precipitated. Then it gets filtered, and then we're left with this filtrate that now just contains copper, zinc, and lead. And what happens is this gets diluted to a final volume of 250. So we have this big beaker, 250 milliliter solution with copper, zinc, and lead. And what we did is we split this into 3 different aliquots. So that just means 3 different samples, and we did some different things with them. So for this first sample, this first aliquot, we see that we have 15 milliliters of the solution that gets buffered and titrated with 38.43 milliliters of this EDTA solution. There's no masking that's happening here, so we have all 3 of those metals in the solution. But for the second one, we have this 20 milliliter aliquot, and here the problem tells us that thiosulfate was used to mask the copper. So because that copper is being masked, we only see lead and zinc in the sample. And so this gets titrated with 34.10 milliliters of this EDTA. And in our last sample, we have this 25 milliliter solution, and it tells us that cyanide was used to mask the copper and the zinc. So now we only see lead in this sample. And then this gets titrated with this 29.95 milliliters of 0.00154 molar EDTA solution. And so with all of this information, we want to find the composition by mass of each metal in this original pewter sample. So this seems kind of complex, but I'm going to walk us through each piece, and we're actually going to be just fine. Now, one thing that's going to be really important to note that will help us with solving this is that EDTA to metal is always a one-to-one like complex, right? And so with this in mind, then we can say that the moles of EDTA in each of these samples equals the moles of the metal. So for example, for aliquot 3, our moles of EDTA equal moles of lead. So that's an easy place to start. And then kind of working almost backwards with aliquot 2. Oh, this one does not have a label. Okay. For aliquot 2, moles of EDTA equals moles of lead plus zinc. So moles of lead plus moles of zinc. And then same thing for aliquot 1. Moles of EDTA equal moles of lead, copper, and zinc. And so I'm going to start with aliquot 3 just because it seems the most simple. So let's go ahead and just start with finding the moles of EDTA in this third aliquot. So for aliquot 3, moles of EDTA equals 0.02995 liters times that concentration. And this is just coming from this part of the problem. And this should tell me 4.6123 times 10 to the negative 5 moles of EDTA, which we know equal our moles of lead because it is 1-to-1. Now, what's important to note is that this equals our moles in this 250 milliliter sample. 25 milliliter sample, but it does not equal our moles in the 250. It's been diluted. So we need to take that into account. So I'm going to take 4.6123 10 to the negative 5 moles, divide that by the 25 milliliters, multiply it by the 250, and that should give me 4.6123 times 10 to the negative 4 moles of PB in our pewter sample. All right, so that's good. We've pretty much found what we need to get the mass percent of, well, we've found what we need to get at least our grams of PB from here, or of lead from here. But what's going to be nice is that we can use this value in the next calculations for the other aliquots. So let's go ahead and move to aliquot 2, and I'll show you what I mean. So for aliquot 2, I'm going to start the same way, where I want to find my moles of EDTA. So here, I'm going to do 0.03410 liters times that concentration. And I have 5.2514 times 10 to the negative 5 moles of EDTA. So that means I have 5.2514 times 10 to the negative 4 moles of PB plus zinc. This is a 20 milliliter sample, yeah. In a 20 milliliter sample. And so again, I'm going to take into account that this has been diluted. So I'll do this divided by 20 times 250. So I finally get that I have 6.56425 times 10 to the negative 4 moles of Pb plus zinc in the pewter sample. Alright, and I'm going to do the same exact thing with aliquot 3. So I'm just kind of repeating the same steps over and over at first, and that's okay. Oh, aliquot 1. Alright, so here we have moles of EDTA equals 0.03843 liters times 0.00154 molar, which should be 5.9182 times 10 to the negative 5 moles. Again, EDTA, but we know that 5.9182, that this also equals my moles of Pb, copper, and zinc. I'm going to take into account this dilution, 50 milliliters times 250 milliliters. And so I'm going to have 9.8637 times 10 to the negative 4 moles of copper, of lead, copper, and zinc. Ooh, that's hard to see. I'll go with yellow. It's better. Alright. So, we have quite a good bit of information already. But what we can do is we can use this info to figure out how much of each metal is in the sample. So, let's start with, we can start with 3, aliquot 3. We can start with lead because that one is the most simple. So if I had 4.6123 times 10 to the negative 4 moles of lead, and remember this comes from aliquot 3, what I can do is I can use the molar mass to get the grams, and then use that to over the grams of the total pewter times 100 to get the mass percent. So from the periodic table, 207.2 grams of lead are in 1 mole. And this is going to tell me that I have 0.095567 grams of lead. And if I divide that by the total mass we started with, so this value right here, 0.4477, of pewter times 100, this is going to tell me that I have 21.35% lead. Okay, that is one of them already found. Now we can do the next two. So what I'm going to take into account is let me see how I want to word this. Let's start with what we have from aliquot 2 and aliquot 3 to see if we can find the amount of zinc we have. Let's just start with that. So, if I have 6.56425 times 10 to the negative 4, and this is moles of Pb plus zinc. If I take this and I subtract what we already know. So in this case, we already know what lead is, right? I mean, it's literally right above what we're looking at. I can go ahead and subtract how much of the lead that we already know is in the sample, and that'll tell us the remaining amount of zinc we have. So I'm going to subtract this from, or I'm going to take 6.56 and subtract 4.6123 times 10 to the negative 4 moles of lead. This tells me that I have 1.95195 times 10 to the negative 4 moles of zinc. And this is great because now I can get my mass percent of zinc. So, do it the same way we just did for the lead. Okay, moles of zinc. And from the periodic table, we should get that 65.38 grams of zinc are in 1 mole. So that means we have 0.01276 grams of zinc. Take that over the total, 4477 grams of pewter, times 100, and that means I have 2.85% zinc. Great, we've solved a second part of the puzzle. Alright, now I'm going to do the same exact thing, but with the information we have from that first aliquot. So, if we know from the first aliquot that we have 9.8637 times 10 to the negative 4 moles of lead, zinc, and copper. What we do know, now there's a few ways we could do this, right? We know our lead and we know our zinc now. So I could take this and I could subtract from the individual moles we found. But to make our lives just a little bit easier, if we know that we're looking for copper, if we know that lead and zinc is this value, we can just go ahead and plug it in here. If we subtract the moles we have for lead and zinc from aliquot 2, then it's going to leave us with the moles of copper from aliquot 1. So I'm going to say minus 6.56 times 10 to the negative 4 moles of Pb and zinc. So as you can see, it gets rid of these, and I'm just left with copper. And that's going to tell me that I have 3.29945 times 10 to the negative 4 moles of copper. And this is great because, again, we can find the percent of copper now. So I'll do it the same exact way. 3.29945 times 10 to the negative 4 moles of copper. Copper is 63.546 grams per 1 mole. And so this is going to tell me that I have 0.020967 grams of copper. Divide that by the total mass. Times 100. And this is going to be 4.68% copper. Okay, we have 3 out of the 4 that we need. We have lead, copper, and zinc. We now just need to get the amount of tin that was left. And since we know that this should all equal 100%, I'm just going to take 100% minus 4.68% for our copper, minus 2.85% for our zinc, and then minus 21.35% for our lead. And this should tell me that I have 71.12% tin. And that's it. I have everything I need. So it was kind of complex, but the things that made it easy were, first, making my little doodle. This little doodle up top, drawing it out, annotating what the problem was telling me, let me realize that I'm really just working with 3 titrations, which at this point, hopefully, we understand titrations a good bit, so we know what we know from here. Another thing that helped was knowing that EDTA to metal is always 1-to-1. That let us relate our moles of EDTA to moles of each. And then from there, it's kind of like a puzzle. I think this is kind of fun. You have to figure out what fits in. I always started with the one that has the least amount in it, just because it was the easiest for me, but really you can start anywhere. But yeah, starting with finding the moles of EDTA in each solution, so then you find the moles of each metal in each solution, and then kind of trying to relate them till you get to your final percentages. Right, so for the last question I'm going to work in this video, I'm going to do question 10 from the review cards, which is calculating PFE2+ at each point of the titration when 25 milliliters of 0.02110 molar Fe has been titrated with 0.03564 molar EDTA at a pH of 6 at the following points. So I've got 3 different points. So again, this is just another titration with some slightly different rules, but we're going to start the same. We're going to write the reaction that we need. So in this case, the reaction is Fe2 plus EDTA gives me FeY2 minus. Now, whenever we're working with EDTA, there are now a few more things that we need to consider on top of this and VE, which I'm now realizing I didn't find VE. So let's go ahead and find VE. So we'll do 25 milliliters times 0.02110 molar, and then 0.03564. All right, VE is 14.80. Okay. Again, those are the same first steps we've done for the last few titrations, but there's another extra step that we need to take into account when we're working with EDTA, and that's writing that K prime F expression. So remember that Kf prime is this alpha Y4 minus times the Kf, and that this equals that equilibrium expression, but we'll get there in a second. Okay, so these values are going to come from some tables. So we know that the alpha Y4 minus is 1.8 times 10 to the negative 5, and this comes from, let me see what table this is. This comes from the table 12, and it's specifically at a pH of 6. This is our alpha Y4 minus. And then the next one, this Kf is going to be 10 raised to the 14.30. And again, this comes from a table where it gives you the log Kf values. This is technically table 12.2. So it tells us the log Kf values for each of the metals that we might be using. And so for our case, that was 14.30. And so to get it out of log, I'm going to do 10 to this value. Okay. And this tells me that Kf prime equals 3.6 times 10 to the 9. And that does seem like a large number, but that is what we're looking for in this case. All right. So if we're going to look at part A, this is 10 milliliters of EDTA have been added. So the first step is wondering, okay, where are we? At this point, we are before VE. All right, so we're actually, what, just 10 milliliters before VE? No, 14 minus 10 is like 4 milliliters before VE. Okay, but to solve this part of the problem, what we need to remember is what is in our solution. So at this point, we have excess of that Fe2+. We have not added enough EDTA to be at equilibrium. So we have excess of that complex, the iron. And so what we're going to do is very similar to what we've done in the past, and it's going to be the Fe2+ equals, we're going to do the fraction remaining, which if we remember, it's VE minus V added over VE times the initial concentration of that metal, and then by that dilution factor, which is just VI over V total. So in this case, we're going to have 14.80 minus 10 over 14.80. Our initial iron concentration was 0.02110. And then our total, this is initially we had 25 and now we have 35. And this tells me that my iron concentration is 0.00489. So when I plug that into the negative log, I'll do it over here. PFE, the negative log of 0.00489 tells me that the PFE is 2.311. Okay, so what was important to note was that when we are before, in this case, when we have excess, this is what we're going to be using. The next point is at VE, so that means we have added 14.80 milliliters of EDTA. And so what we're going to want to do here is we're going to want to use that equilibrium expression, and that typically looks like a Ka or Kb equals x squared over F minus x. Now it's going to look slightly different for when we have EDTA, so let's write out that equation again. Fe2 plus EDTA gives me Fey2 minus. So it's gonna be just slightly backwards, where this is the F and it has been diluted minus X. So we need to be able to use Kf prime equals F diluted minus X over X squared. Now, thankfully, we already found Kf prime, so I'm just gonna rewrite that over here. Kf prime equaled, what was it? Let's see. 3.6 times 10 to the 9. So we just need to find this F diluted, which is going to be relatively simple. We just need to figure out the moles we have. So at this point, virtually all of the metal that we have is in this form of Fey2 minus. So our moles of Fey2 minus is going to equal the moles of Fe2 plus initially. So in that case, that's going to be 0.025 liters times 0.0211 molar, which gives me 5.27 times 10 to the negative 4 moles. But remember, this has now been diluted. We've added some more. We've added that ETA, so it's not the same amount of moles, right? We started with 25 milliliters, and now we're well above that. So we're going to say that the concentration of Fey2 minus is this moles, 5.27 times 10 to the negative 4, over our current total concentration, or not concentration, current total volume, which is 0.0398 liters. So this is 0.01325 molar Fey2 minus, which equals that F diluted that we're looking for. So now I'm just going to plug this into that equation. So I'll say 3.6 times 10 to the 9 equals, and we can use that approximation in this case. I know it looks kind of different, but we're still able to do that. So we're going to do 0.01325 over x squared. So then we end up getting that x becomes the square root of 0.01325 over 3.6 times 10 to the 9. And x equals 1.9 times 10 to the negative 6. And like I said earlier, we always need to check and make sure that we know what x equals. So in this case, x equals Fe2 plus. So we're going to just go ahead and plug it into that PFE. PFE equals the negative log of 1.9 times 10 to the negative 6. And it equals 5.72. So this is very similar to what we've seen where, we use that Ka or Kb, but we just need to switch it up just a little bit to make sense for EDTA. Okay, this last one is 18 milliliters of EDTA have been added. So now we are past VE, or after VE. And what we're going to want to do here is, again, remember what we have in our solution. So at this point, it has excess EDTA, and virtually all the metal is in the form of that FeY2-. But what we need to do is we're going to use that similar KF expression, but let's write out what this looks like currently. So if we have Fe2 plus EDTA gives me FeY2-, that stays the same. And so Kf prime is going to equal FeY2- over Fe2 plus times EDTA. And we can't just make these x's because they're not equal at this point, right? We're past the equilibrium point, so we're going to have more EDTA than we do of that Fe2 plus. But let's figure out what we do know. We know Kf prime, we've already found that. We can easily find FeY2-, so let's go ahead and find that. So what we're going to do is we're going to take the moles of FeY2-, which we had found earlier. It's right here. This 5.27 times 10 to the negative 4. 5.27 times 10 to the negative 4. This is the moles. And we just need to divide this by our new total volume. New total volume. Ooh, what's happening? Let me rewrite that 1 second. Alright, this equals 5.275 times 10 to the negative 4 over, we are now at 0.043 liters, which tells me this is 0.01227. Great. And so that means we have this. We know that this is what we're looking for, and we can find EDTA. We're going to find EDTA in excess the same way we found excess in the past titrations. So EDTA is going to equal to the initial amount of EDTA that we've had times that dilution factor, which is going to be V excess over V total. So this is going to look like 0.03564 times, we are 3.2 in excess, and we have a total of 43. So it's 2.65 times 10 to the negative 3 molar. So yeah, now we do for sure have this. So we can plug everything in. So let's see. We know Kf. Kf prime. I just have to remind myself of what it is. Let me find it. There it is. 3.6 times 10 to the 9 equals, let's see. We have FeY2-, that is going to be 0.01227. We're looking for Fe2 plus, and we have this concentration of EDTA. That's 2.65 times 10 to the negative 3. We can do some rearranging, and we'll solve for Fe, and we should get that Fe2 plus equals 1.258 times 10 to the negative 9. So that means P of Fe equals 8.89. And just like that, we have solved, once again, another titration, but this one with EDTA. So the things we needed to know were, whenever you're titrating with EDTA, how do you solve before, at, and after VE? So hopefully this helped a little bit. I'm sorry for having to cancel the in-person and online review. It has some stuff going on, but I hope that this helps. Feel free to send me an email if it does not, and I wish you all the best of luck in studying. See you later.